of Tiffany Luong. She's going to have, Tiffany, you will have 45 minutes presentation. After we'll go for the questions. And the title of your PhD is Towards the Exploitation of Mental Work in Virtual Reality. Let me present the jury member. So we have as a rapporteur Anthony Sid from University College of London, Daniel Mestre, a CNRS at Aix-Marseille University. As examiner, we have Mark Billinghurst from University of South Australia, myself, Catherine Pelachos, CNRS is here at Sorbonne University. Then we have your advisors, you have 4 of them. There's Ferran Arguelaguet at INRIA de Rennes, Bretagne Atlantique, Martin Nicolas, IRT BICOM, Guillaume Gégou, IRT BICOM, and Anatole Lécuyer, INRIA de Rennes, Bretagne Atlantique. All right, so I think we can start the presentation, and I will give you the floor for 45 minutes, and we start with the question.
So, hello everyone, and thank you for these introductions. And thank you all for being present today during this defense. I'm going to introduce you my PhD work to go towards the exploitations of mental workload assessment in virtual reality systems. So my PhD is supervised by Anatole Lécuyer, and this PhD was funded by the Institute of Research and Technology BICOM. So I was also supervised by Guillaume Gégou, Ferran Arguelaguet, and Nicolas Martin. VR systems are becoming increasingly popular in many fields, whether it is in the entertainment field, for video games, for example, whether it is in the therapeutical field, for example, to treat PTSD, phobia, or anxiety, or in the training field to simulate complex real-world situations. I'm going to put the focus a little bit more on the training field today. And well, VR is particularly convenient in the training field as it provides an opportunity for people to train in environments that are otherwise impossible, far too risky, or far too expensive. So if the video will start. So we had an example, for example, for fire workers. So basically, this is a very dangerous situation, and VR is going to be able to simulate this kind of situations in a safe way. Research has shown that VR could improve learning retentions compared to more traditional supports, for example, compared to computer screens or compared to paper and pencil supports. And this is particularly important in fields such as in the aviation industries, as you have lives at stake. And the goal of most of these VR applications usually are to train users in order to decrease the number of workplace accidents and or to improve the user's learning performances. The issue is that these studies are mostly interested in learning and task performance outcomes. So they want to make sure that the training applications are going to be efficient. And most of the time, they are not going to take into account the user's cognitions or physical measures in their VR applications, which is where quite important as human factors is one of the main issue in and the main cause of flight accidents. And this is also the case in VR training applications. So what we want to do actually is to adapt VR applications content based on the user psychological state. And more particularly, we want to adapt the VR application based on the user's mental workload. So we want to go towards the exploitations of mental workload measures in VR applications in order to make the applications more fitted to the users. I'm going to explain a little bit what is mental workload. So actually, mental workload is a psychological concept, which is quite easy to understand, but a little bit hard to define. There is no real consensus over its definitions, even if some parts stay the same in most of these definitions. I'm going to give you a descriptions made by Weekends in 2002. So mental workload describes the relations between the quantitative demand for resources imposed by a task and the ability to supply those resources by the operators. So in most definitions, you often have on the one hand, the user's cognitive resources, and you have on the other hand, the task cognitive demands. So if I ask you to solve these equations, so find x for 4x equal to, you're likely to be underloaded because you will agree with me, it is very easy. And if I ask you to do this task, you will have a lot of remaining cognitive resources left. On the other hand, if I ask you to solve these equations, and well, I can promise you that it's going to be very difficult and you're likely to be overloaded. So this is a Fermat-Last theorem, and actually you don't have any solutions. So you won't be able to do another task in parallel to this task. So mental workload is a variable that we want to keep under control, whether it is to keep the users focused and engaged in their task, or whether it is to train users to situations where they might be overloaded. Our objective is to go towards exploited systems, and for that, we decided to decompose the research axis in three. First, we have the inductions of mental workload in VR. Then we have the recognitions of mental workload in VR, and then we have the exploitations of mental workload in VR. For the inductions of mental workload in VR, we are going to focus on the influence or the effect of VR stimuli on the user's mental workload responses. So we are going to be able to measure the user task performance measures, for example, and physiological measures, for example. For the recognition of mental workload, we are going to focus on doing and working on a recognition model, which is going to be able to recognize the user's subjective mental workload level or perceived mental workload level without asking the users how they are feeling. So we want to use objective measures, and we want to use these objective measures to be able to recognize the user's subjective mental workload level automatically. For the exploitations of mental workload, we are going to use the recognized mental workload level or mental workload measures, and we are going to try to adapt VR stimuli in order to induce a targeted mental workload level. So it's going to be the adaptation logic. So we did 3 main contributions and 5 user studies, starting with a study of mental effort in virtual versus in real environments. So we did 2 user studies, and we wanted to study the effect of wearing a VR HMD on the user's mental effort. So we just targeted the induction part of the loop in this case. For the second contributions, we proposed a methodology to introduce mental workload assessment in the design of VR training scenarios. So we targeted the induction part because we wanted to see the interaction effect between different types of tasks in VR. And we targeted the exploitations of mental workload because we wanted to use mental workload assessment in order to be able to modulate the user's mental workload over time. For the third contributions, we focused on proposing an all-in-one solutions to do the real-time recognition of mental workload using physiological sensors integrated into VR HMD. So first, I'm going to introduce you a little bit of state of the art, and starting with the introduction of mental workload in VR, then the recognition, and finally the exploitations. For the induction of mental workload in VR, we can decompose work studying the induction into 2 categories. First, methods of inductions. So those are going to be used in order to study human behaviors or differences between 2 or more conditions, considering, for example, the mental workload level or cognitive task performances. So there are going to be methods which are going to be able to modulate the user's mental workload levels, and we are going to be able to use them, for example, to train mental workload recognition models. For the second point, so we are going to focus on factors influencing mental workload in VR. So we are going to study what is the effect of some parameters and some factors on mental workload measures. For methods of inductions, so we mainly have cognitive tasks used in VR. So you have, for example, spatial manipulation tasks. So we are going to make use of the 3D in VR to manipulate 3D objects. And we are going to measure task performances and different mental workload measures. You have some studies which adapted the Stroop test in VR. And you have the very famous N-back task, which is relying on the working memory, the user's working memory. And we are going to be able to modulate the difficulty of the N-back task very easily to induce different mental workload levels. So I have quite a lot of studies on this task, which are all standardized. And you have a lot of other cognitive tasks, but I'm not going to detail all of them today. As for factors influencing mental workload in VR, you have redirected walking, which was found to increase cognitive demands, depending on the angle of the redirections. You have the control of a self-avatar, which was found to influence the user's cognitive task performance, considering a later recall task. And you have the avatar appearance, which can influence the user's mental workload levels. So being embodied in Einstein's body is going to increase the user's cognitive task performance compared to being embodied into a normal looking avatar. So one question we might ask is, Well, we consider most of the time single standardized task in VR to be able to moderate the user's mental workload, but how it is when we want to consider multitasking, because we are going to be able to stimulate different cognitive resources in the brain. So we would like to propose a way to use multitasking to induce mental workload in VR. And that's going to be one of the points we are going to treat in the second contribution. As for factors influencing mental workload in VR, we might be asking already, is using VR devices and being immersed in a virtual reality environment is going to have an influence on the user's mental workload measures? And that's going to be the research question of the first contribution. For the recognitions of mental workload in VR, so I'm going to present you the different methods to measure mental workload in VR. So this is not an easy task, and many of these measurement methods have advantages and disadvantages, which can be discussed. So you have the very popular self-report methods. So basically, those are going to be questionnaires, and we are going to ask users how they are feeling. So you have the very, very famous NASA TLX, developed by Hart and Staveland in 1988. You have the subjective workload assessment techniques, and both of them are going to be multidimensional scales. So they are going to take time to answer, but they have very high, they are very qualified to measure the user's mental workload. So they are very detailed. And you have unidimensional scale, which are quicker to respond and which have found proved their validity, such as, for example, the ISA scale and the rating scale of mental effort. We can also measure the user's task performances, so the accuracy and the reaction time, but it's going to be a little bit less sensitive to the user's mental workload. And you can analyze the facial expression of the users, the body gestures, and for example, for the eye behaviors, the number of blinks and the fixation durations. A very, very popular way to measure the user's mental workload in VR and outside VR is to use the psychophysiological measures. So psychophysiological measures are going to be physiological responses to psychological processes. So we can measure, for example, the brain activity of the users using EEGs. We can measure the brain activity using FNIRS. We can measure the skin conductance level using epidermal activity sensors. We can measure the user's heart rate activity, and we can also measure the user's pupil diameter. Usually, what we are going to do is to use data fusion methods to classify the user state. So this was proposed by Rosa and Picard from the MIT in 2001 for emotions particularly. And basically, it means that we are going to take the physiological signals, we are going to extract physiological features, and then we are going to take these features in order to try to classify the user's emotions and psychological states. So there are more and more works and companies which are trying to integrate the physiological sensors directly into the VRHMD because, well, it is more convenient to just deal with one headset and not all of the user sensor wires and everything. So for example, you have the MIT Media Lab, which developed the PhysioHMD, which is a module which can be integrated into VRHMD and AR headset. So they integrated EEG sensors, epidermal activity sensors, and other kind of sensors. OpenBCI and Valve are working on a VR headset which integrate EEG sensors. So this is a work in progress, which should be presented in the following years. And you have a lot of other headsets which integrate EEG sensors, such as, for example, Neurable or Lucid VR. And as you know, there are a lot of headsets which integrate eye tracking solutions. So the Vive Pro Eye, Fove, and a lot more. One question we might ask is, among all of these measures, which kind of measures should we take into account to try to recognize the user's mental workload in VR? Which one works the best? So should we consider skin conductance level? Should we consider heart rate activity or task performance measures to try to recognize the user's mental workload? Also, does integrating the sensors directly inside the VRHMD has an impact on the mental workload recognitions, since this is something that is interesting us? So we don't know if it's going to have to be more robust or not, or if it's going to be to decrease or increase the mental workload recognition accuracy. In the literature, we didn't really see in the past work which dealt with the recognition in real time in VR. And that's something that we are going to try to tackle in the third contribution. For the exploitations of mental workload in VR, we can decompose them in two categories. So as a reminder, the exploitation is going to correspond to the adaptive logic. And so we can have explicit feedback and we can have implicit feedback. In both cases, we are going to measure the user's physiological activities or other objective measures. So for example, task performances, and we are going to use these measures in order to adapt the virtual environments. And in the case of the explicit feedback, the user is going to be aware that the feedback they are receiving in the virtual environments are going to be based on their physiological signals or the other objective measures. And in the case of the implicit feedback, the user is not going to be aware that their measures are going to be used to adapt and to provide feedbacks from the virtual environment. So we can decompose and subdivide the explicit feedback into two categories. The very famous biofeedback categories. So in this case, we are going to focus on especially physiological signals or biosignals, and we are going to ask the user or to invite the users to control their physiological signals based on the feedback which is presented in the virtual environments. So it is quite a lot used in the clinical and therapeutical field, for example. So we have Van Rougy and colleagues who try to regulate or to try to invite children to regulate their anxiety. So here you can see a circle in the center, and this circle is going to vary in size based on the user's breathing activity. For the second subcategories, we have physiological displays, and in this case, we are just going to have a direct feedback of the physiological activities in either the user interfaces or either in the experimental interfaces or in another user interfaces. So in this case, the user is not going to be invited to try to control their physiological signals. It's just going to be informative. For example, you have a Dia and colleagues study. So they developed a multi-user applications, and in these applications, one of the user had a feedback of the other user heart rate activity. So the feedback was mostly informative, and it communicated the physiological state of the other user to one of the users. For the explicit feedback, so I'm going to focus on VR training. So most of the studies focus on adapting a single task difficulties based on the user's task performances. For example, on the left, you can see Grimm and colleagues study where they adapted the distance between the basket and the ball based on the user's task performance. And you have other studies which adapted the difficulty of a single task based on physiological signals. So in this case, Dia and colleagues studies adapted the visual search task difficulty based on the EEG alpha band power. One question we might ask is, how do we adapt the immersive virtual environment contents in the case where we have multiple tasks in parallel? So how do we adapt immersive virtual environment in complex contexts? Should we decrease or increase the difficulty of one specific task or another task, depending on the task performance? And how do we take into account the user's perceived mental workload level? So task performance is not very sensitive sometimes to the user's mental workload, and this was proven by Dia and colleagues study. And so we are going to tackle this question in the second contribution. I'm going to start now detailing the contributions and some of the results we obtained during the PhD. So I'm going to focus on the main results. So for the first contributions, we studied the user's mental work effort in virtual reality. And we wanted to answer these questions. So does being immersed in virtual environments using a VR HMD is going to influence the user's mental effort? So we did the first experiment where we had 27 participants, and we went a little bit further. So we did the qualifying studies with 25 participants. So we manipulated 3 independent variables. So starting with the end-back task. So we had the one-back task, the two-back task, and the three-back task. So we had 3 difficulty levels. And we asked users to press the trigger button of the Vive controller if and only if the letters they heard in the audio headset was the same as the end's previous one. So the user heard sequences of letters, and for example, for the two-back task, if the users heard A, B, A, they had to press the trigger button because A was the same letter as the second previous one, etc. So similarly. And we manipulated the secondary task, the presence or not of a secondary task. So the users were either sitting or walking. and the environment. So the user were either in the real environments or in the virtual reality environments. And those were within subject conditions. So in the Sitting X real environments, the user heard sequences of letters in the audio headset. They were seated in front of a TV, and they could see the difficulty of the n-back task displayed on the TV. After each difficulty of the n-back task, they were asked to report their mental effort on a scale. So I'm going to detail you a little bit more the collected data afterward. In the virtual reality conditions, so Sitting X VR conditions, as you can see, we did a very high fidelity representations of the real environments in VR. And it was exactly the same task. So you had the difficulty of the n-back task displayed on the virtual TV, and they still heard the sequences of letter in the audio headset. In the Walking X-ray environments, we asked the user why they were doing the n-back task to walk in circles in the orange rectangle. They were asked to walk at their own pace, so in a very natural ways, so it didn't really bother them. And in the VR conditions, so as you can see, everything was calibrated. So when they walked in the virtual environment, they should have the same feedback as in the real conditions. So we collected several types of measures, starting with the subjective mental effort using the rating scale of mental effort. So they had to rate their mental effort between 0 and 150, and then to click on the following buttons to start another task. We also collected the user's n-back task performance, so we recorded the accuracy. And we also recorded the pressure exerted on the trigger button while they were doing the n-back task. So we did a homemade sensor with an Arduino card to send the data to the computer and a force-sensitive resistance sensor. And we also recorded the user's response time to the n-back task. We also assessed the user's heart rate activity and the skin conductance level, but only in the first experiment and not in the second one. So on the left, you can see the rating scale of mental effort, so the measures of the user's subjective mental effort. And on the right, you can see the task performance measures. So here are the result in the real conditions. And as you can see in the virtual conditions, so we didn't find a significant effect of the environments on the user's mental effort and on the accuracy. So wearing a VRHMD, considering the sitting and walking condition, didn't increase the user's mental effort. We found out that walking significantly increased the user's mental effort, which was to be expected because when the user was walking, so it was a secondary task, but still it was a very easy task. And the fact that it significantly increased the user's mental effort means that we have to control the amount of interactions we have in the virtual environments. So in the second experiment, we wanted to take a step further. So we fixed some variables. So the walking task, and we only consider the walking task and the two-back task. And we wanted to make sure that in these conditions, consider only the walking task and the two-back task, we wouldn't have any effect of the environments. So it was a qualifying studies. Also, we wanted to find out if after having put on the VRHMD, the user were going to experience more mental effort or not, because they will have to be accommodated to the virtual environment. So here are the result, and as you can see, so this is an indicator of time somehow in the virtual condition and real conditions, and we didn't find any effect of the accommodations to VR on the user's mental effort. So here we could have expected this point to be higher, considering the mental effort, but it was not the case. It was very stable inside the same environment for the two-back task. But in these conditions, we found out that we had an effect of the environment on the user's mental effort, considering only the walking conditions. So as you can see, we had a small increase, but still it was a significant increase. And so VR users experience more mental effort in the VR conditions than in the real condition. So we led 2 user studies to study the difference of mental effort in virtual versus in real environments. And our results support that wearing a VRHMD has a limited impact on the user's mental effort. Especially, we didn't find an effect in the sitting conditions, but we found an effect in the walking conditions. So this might be due to the fact that in the virtual conditions, the user didn't have any feedback of their body. We didn't use an avatar, so they didn't have any virtual body. And the fact that they couldn't see their feet in the virtual condition might be the reason why they experience more mental effort. Also, we have to control the amount of interactions and the amount of movement the user might do in the virtual conditions, because those might increase the user's mental effort. So walking increases the user's mental effort. So if you want to study different conditions on the user's mental effort and the users are moving differently, you have to control that. The response time, pressure exerted on the button, and the heart rate, which were the objective measures we collected, could be used as indicators of the user's mental effort, considering the fact that we have to take into account that the movement, and so because of the movement, we can have some motion artifacts. So it was the case, for example, for the heart rate. So for the second contributions, we proposed a methodology to introduce the mental workload in the design of complex training scenarios. So that was a research question we wanted to answer. So we decided to propose an approach depending on three main steps. So first, the state machine generations. So we had virtual environments. We wanted to identify the different tasks inside these virtual environments. And we wanted to identify the different difficulty levels inside each of these tasks. Based on these different task difficulty, we wanted to associate them together to form states of state machines. So we wanted a state machine with the different possible task configurations. Next, for the mental workload assessment part, we wanted to measure the effect of the states on the user's mental workload and to put these mental workload measures inside the states of the state machine. Finally, for the scenario generation part, we want to use the state machines and the mental workload assessment inside the state machine in order to generate scenarios which are going to be able to modulate the mental workload over time. We developed a VR flight simulator in Become with a true-scale hardware part which matched the virtual cockpit in size and positions. And the user were instructed to go through the green circles, so the green circles there, and they were asked to follow the green line as closely as possible. So as you can see, the user were piloting the aircraft using the joystick with their right hand, and they were interacting with the different virtual interfaces with their left hand and the Vive controller. So we developed 3 tasks inspired by the MATB2, which is software developed by the NASA to study the operator's mental workload. And we decided to keep 3 main tasks. So the piloting task, and we modulated the piloting task difficulties by changing the speed of the aircraft and by increasing or decreasing the number of circles the users could see at a time. So somehow we manipulated the visibility of the trajectory. For the radio task, the user were asked to change the radio frequency depending on the audio message they were receiving in the audio headset. So this task was either deactivated or activated. And for the field task or resource management task, the user were asked to maintain 2 tanks levels inside an appropriate zone using different pump buttons. So it was the same as the radio task. So it was either deactivated or activated for the difficulty. So we used all task difficulties and we generated the state machines. So 3 by 2 by 2, we obtained 12 states inside the state machines. And this state was supposed to be the easiest one. And this state was supposed to be the hardest one. So going now into the data assessment part, we collected several types of measures. So first, the subjective mental workload assessment using the ISA scales. So the ISA scale is a scale with 5 different ratings. 1 meaning that the user is underloaded, that the users have a lot of remaining cognitive resources left. And 5 meaning that the users were overloaded and they could not complete the task completely, or it was quite difficult for them to do it. So we ask users to report the self-report their mental workload levels when the windows appeared in front of them. And these windows appeared every 30 seconds, basically, and 3 times per state. We also recorded performance and behavioral measures, but I'm not going to present you the result today. And we had 38 participants for the data assessment part. So we made users traverse all 12 states of the state machines in a randomized order. And in the end, we obtained the following map of mental workload levels inside the state machines. So in light blue, it means that the user's mental workload level was in average very low inside the state when they were exposed to the state inside the state machines. And the lowest state was 1.5 by 5 being the maximum. And the maximum average ISA level they experienced in average was 4.13. So we used the state machines to generate different scenarios. And so for the first scenario, we wanted to induce a medium mental workload level along to the users. So we chose the 5 states the closest to the ISA equals 3 inside the state machines. For the second scenario, we wanted to induce a surprise effect inside the scenarios. So we chose the 4 lowest ISA state, and we finally chose the one with the highest ISA state. And for the third scenario, we wanted to induce a progressive increase of mental workload over time. So we chose the lowest ISA state, the highest ISA state, and we chose the lowest transition cost between each state from the lowest to the highest. So here's the result for the first experiment. So it was for the data assessment part. So it was when all users traversed the 12th state of the state machine in a randomized order, and this was the mental workload progression we expected for each of the 3 scenarios we designed. So in this case, we had 38 participants who traversed the state machine in a randomized order. And here are the results for the second experiment when users traversed the state machine in a fixed order for each of the scenarios. So as you can see, we didn't find any significant effect between the first experiment and the second one, meaning that we managed to induce the expected mental workload progression over time. So we proposed a methodology to introduce mental workload assessment in VR training scenarios, and the scenario we designed using our approach were able to induce expected mental workload progression over time. And we had very interesting answer and results for the delays in response, which can impact the user's perception of the progression over the scenarios, but I'm not going to present this result today too. So for the third contribution, we proposed an all-in-one solutions to recognize in real time the user's mental workload levels in VR using physiological sensors directly integrated into a VR HMD. So we wanted to compare also different supervised learning setup on the user's mental workload recognition accuracy, because we decided to use supervised learning and more particularly the random forest algorithm to train the mental workload recognition models. So we wanted to classify different mental workload levels based on objective measures and based on previous tests, while random forest works especially well. So we wanted to compare different setups, and we wanted especially to see which sensor works the best to train the mental workload recognition models. So we trained different mental workload recognition models using sensors individually and different association of sensors to see how they interacted between them. And we sort of made a benchmark about which one works the best in our conditions on the mental workload recognition accuracy. Next, we wanted to see if integrating the sensors directly into the VRHMD was going to impact the user's mental workload recognition accuracy compared to commercial grade systems. So here we decided to use the shimmer bracelet, which is quite spread in the academia world and in the industry. And we wanted to compare different signal normalization methods to take into account the individual differences between the users. I'm going to focus more especially on these 2 parts. And so for how did we integrate the hardware and the sensors inside the VRHMD? So we use an electronic card to stream the data to the computer. We have put this electronic card inside a 3D printed case, which was placed in the back of the VR headset. And in our case, we decided to use the HTC Vive Pro Eye, which has already an eye tracker embedded inside it. And we integrated a PPG sensor to measure the user's heart rate activity and a skin conductance sensor, so 2 electrodes to measure the user's skin conductance level inside the VR headset. So we had 75 participants, and we used the previously developed VR flight simulators and the previously developed methodology we proposed in order to try to induce balanced classes of mental workload levels. We had predictor variables, so many objective measures, and so we had physiological signals. So physiological signals from the HMD sensors, from the commercial grade sensors, so the shimmer bracelet, and the pupil diameter from the Vive Pro eye tracker. We also recorded the user's piloting task performance, so the distance to the trajectory when the user passed the circles. And we tried to predict the user's subjective mental workload scores, so using the ISA scale. So we wanted to predict 4 classes of users' mental workload, so 1, 2, 3, and we merged 4 and 5 to have balanced classes. We synchronized the subjective mental workload score with the objective measures, and based on the subjective mental workload timestamp, we extracted the features before, during the time windows, based on the different physiological signals and the piloting task performances. So in the end, we had a data set where we had objective measures features. So for example, the heart rate, features related to the heart rate variability, to the skin conductance level, or to the task performance. And we labeled each of these objective features with a subjective data, so with one of the 4 classes of mental workload level. We decided to use a random forest algorithm to train the recognition model. And in the end, we obtained a mental workload recognition model. These are the results we obtained. So this is a confusion matrix. And on the top, you can see the ground truth. So the self-reported mental workload of the user reported. And on the left, you can see the result of the recognition model. So the mental workload level is the mental workload level accuracy. So we had a mean recognition accuracy of 65%, which is significantly better than chance level at 25%, considering that we had 4 classes. And this is actually very similar to what we had in the literature. And as you can see, it was quite encouraging to see that when the recognition model was wrong, it was mostly in adjacent classes. And as for the comparison of sensors, so here you can see the mental workload classification accuracy using different models when we used only ocular activity sensors, only epidermal activity features, or only different sensors features. So as you can see, the ocular activity features and the epidermal activity features worked especially well to train the mental workload recognition models compared to the performance measure and to the cardiac activity measures in our context given our applications. And on the right, you can see that when we mix the sensors together, using all physiological sensors or using all physiological sensors plus the task performance measures, we only had a slight increase of mental workload recognition accuracy when we added the task performance measures. This is quite interesting because, well, if you are training a recognition model using the task performance measures, you are not going to be able to use this task performance, this recognition model in another context where you don't have this task performance, this task to do. So using only physiological signals is going to be more generic than using physiological signals plus task performance measures. And in our case, it didn't really add much to add these task performance measures. Also for the comparison between the HMD sensor and the commercial grade sensors, so especially in the mixed measure cases, we had very similar recognition accuracy. And while having the VR, the sensors directly integrated into the VR headset is quite more convenient than using different sensors on the body. For the real-time processing, so we extracted physiological features inside the time windows of 30 seconds. We used these features to recognize the user's mental workload using the previously trained recognition model. And we slided these time windows of 1 second step to update the recognition mental workload level of the users. So here is a real-time interface. And on the left, you can see the physiological signals. So you can see the epidermal activity evolutions over time. You can see the heart rate activity, so the blood volume pulse using the PPG sensors, which is evolving over time too. And you can see the pupil dilations. And on the right, you can see the mental workload predictions. So this is the mental workload recognition's accuracy for each 4 classes we try to predict. And this is refreshed and updated every 1 second, as explained earlier. So we proposed an all-in-one solutions to recognize the user's mental workload in VR in real time using physiological sensors integrated into VR HMD. And we were able to predict 4 classes of mental workload level in real time with 65% average accuracy. And we gave some insight about the impact of the different supervised learning setups on the mental workload recognition accuracy. Basically, integrating sensors inside the VRHMD is going to result in very similar recognition accuracy as using commercial grade systems in our conditions when the user was seated, so maybe more tests will be needed. And the ocular activity and epidermal activity features work especially well to train the mental workload recognition models. And finally, so this I didn't represent this result, but overall normalizations really improved the mental workload recognition models accuracy. So we have to use Bayesian features and to integrate them inside the training of the models to improve the mental workload recognition models accuracy. So for the general conclusions, we conducted we proposed 3 contributions. And in the first contributions, we studied the user's mental effort while wearing a VRHMD compared to in the real environment. And we found out that wearing a VRHMD had a limited impact on the user's mental effort. Interactions and differences in representations, for example, differences in the avatar representations, have to be controlled because they can impact the user's mental effort, they can increase it. For the second contribution, we proposed a methodology to introduce mental workload assessment in the design of VR training scenarios. And the methodology we proposed managed to induce the expected mental workload progression over time. And finally, for the third contributions, we proposed non-Luong solutions to recognize the user's mental workload in real time using physiological sensors integrated into a VRHMD. So the solution we proposed allowed to recognize the user's mental workload with 65% average accuracy. And we gave some insight about the effect of different setups on the mental workload recognition accuracy. For short-term perspective, we could try to study the impact of different factors on the user's mental workload in VR compared to in the real world. So for example, we didn't really assess the effect of latency, frame rate, field of view, which could impact the user's mental workload in some aspects. So there have been some studies which found out that the impact of latency, there was an impact of latency on physiological features. So we could expect the same on the user's mental effort or the user's mental workload maybe. Also, we consider an auditory task for the back task and a visual task for the walking task, but we could try to study the effect of the nature of the task on the user's mental workload in VR, considering the effect of multisensory feedback in VR to see which one is the most important to not trigger any increase in cognitive demands. For the effect of VR devices, so we only consider VRHMD, but you have a lot of different headsets and a lot of different VR devices out there. So you have, for example, cave-like systems, and you have ergonomical factors, which we have to consider because, well, we can expect them to increase the user's mental workload. As for the introduction of mental workload in VR, so we consider discrete task difficulties, but we could try to extend the methodology to continuous task difficulty, which would be very interesting to make it a little bit more generic. Also, we could try to consider other stimuli, for example, virtual agents, for example, guides, other kind of stimuli, so instructions, for example, and we could try to consider collaborative aspects, mixing this kind of methodology with existing frameworks, relying, for example, on Petri nets representation, graph sets, or other kinds of graph networks. For the recognition of mental workload in VR, so we didn't consider brain-computer interfaces measures in the mental workload recognition model, but we know that in the literature, we had very impressive results using EEG of NIRS on the user's mental workload. And we would like to try to integrate this kind of measures inside the VR headset and to compare this kind of measures to, for example, more wearable and the autonomic nervous system activity measures. So heart rate activity, for example, skin conductance activity. Also, we could try to investigate the robustness of integrating the HMD sensors inside the VR headset, considering different VR usages. So in our experiment, the user was seated, but we could try to make the user do different kind of interactions in VR, different kind of locomotions, and see where the sensors, in which place we have to place the sensors for them to be the most robust. And also, we could try to investigate the mental workload recognition model genericity, training, for example, the mental workload recognition model in one specific context, and trying to use this mental workload recognition model in another context. So by leading this work, we wanted to go to our more robust VR applications, which were able to take into account the user's psychological state, and wanted to provide unique experience to adapt it to each users. But while we didn't really close the loop, even if we tackle a little bit of each of these research axes, and there's still a lot more work to do. So for example, for the induction of mental workload, what we could expect to do in the future would be to develop standardized tasks or battery of tasks in order to study the humans and the users' mental workload levels in VR. So VR has a very powerful engagement effect on the users. So we can engage them cognitively and emotionally. And because of that, it could be interesting to try to use all of these opportunities offered by VR in order to try to develop this kind of induction methods. For the recognition of mental workload, so as you know, machine learning and deep learning are making incredible breakthrough in the world at the moment. So it's moving very fast. And well, considering the fact that it's moving very fast, we would have to consider the new methods and the methods which are going to be developed in the future in order to improve the mental workload recognition models. Also, as you know, we don't have a lot of data, physiological data available open source. And it could be interesting to try to make a sort of image database of physiological signals labeled using psychological states. For the exploitations, so as you know, there are very few studies making a loop, so looping and adapting based on the user's psychological state, even if a lot of them are mentioning the fact that that could be very interesting. And well, we will need more user studies in different applications in different fields in order to study if actually taking into account the user psychological state and how taking into account state is going to benefit the users and the user's performance level. So one thing we would like to do in the future is to extend the approach to other affective and cognitive states. So we only consider mental workload in my PhD, but considering emotions, personality traits, and anxiety levels, for example, could be quite interesting and would be the logical next step. So this led us to define a new field of study. So affective and cognitive virtual reality as a study of virtual reality systems and applications that induce, recognize, or exploit affective and cognitive states. And I hope that this work are going to inspire researchers to develop affective and cognitive virtual reality systems and studies. This PhD work has led to papers and presentations in international conferences, a submitted journal paper, and a patent. And I would like to especially thank my supervisors as well as all the people involved in these works. So the participants to my experiment, the hardware engineers who worked on the physiological headset, for example. And this concludes my presentation. Thank you for your attention. I really hope that I managed to keep your mental workload level stable during these presentations.
Thank you, Stephanie, and thank you for keeping up with the time. So now we start with the questions. And we're going to start with rapporteur, and it's going to be Anthony Steed that will ask first a question. So he's professor at the University College of London. Please, Anthony.
Thank you. Good morning. I just wanted to say that I have lots and lots of questions. That's a really good thing, right? I enjoyed reading the thesis, and obviously you covered a very broad area. And done an impressive job of trying to frame it in this nice diagram that you started with, where you have these different understanding mental workload and then trying to induce it and then moderate it. So I will try and do the questions in order through the contributions, though I actually want to focus on the last one for most of the time that I've been allotted. So to start with the first contribution, I wanted to understand and discuss what you think the impacts on mental workload of a head-mounted display should be. Should it be 0? If a head-mounted display gets really, really good, very lightweight, very high field of view, should the mental workload be 0 or not? And we can discuss that.
Oh, that's a very good question. So thank you. So I think that ideally, from an ergonomical point of view, about the weight of the VR HMD, the impact of the field of view, frame rate, and latency, the impact of the headset should be 0 on mental workload. But there's another point that we have to consider. So I don't know if you are all familiar with Yax-Dodson law. Basically, it is a law which shows that the performance of the user is going to depend on their stress level. And we have a similar curves for mental workload. And basically, it means that if the user's mental workload is very low, the user is not going to show great performances. And if the user's mental workload is high, the user's mental workload is not going to be performant. And so we want to be in between, and we want to engage users inside the virtual reality systems in order to make them a little bit more performant. But overall, the impact of the VR headset, I think, should be 0 in terms of ergonomy. And in terms of experience, they should engage the user, so they should somehow trigger a little bit of mental workload. So it is a little bit different. The systems, I think, it should be 0, but the environments, a little bit.
Okay, great. So that would be the contention. Is it's not really about the head-mounted display. It's about what you show on it. So you've purposely chosen a representation of the real environment. So why do that? Isn't that unlikely that you go into VR and do a mental workload task that you in a model of the same environment? Did you do a completely different environment that you put on the head-mounted display? You're in a completely different but similar looking environment, and then would that have a mental workload impact?
So we chose to focus on a realistic environment because we just wanted to study the impact of wearing a VR headset.
Mm-hmm.
And we didn't want to have bias linked to the fidelity of the environment. But I think that eventually we could have sort of an uncanny valley of the virtual environments compared to the real world, and that this uncanny valley could impact a little bit of mental workload effort. So that might be one of the bias that should be discussed actually in our study. But yes, so those are just personal opinion and maybe hypothesis, but yes, I don't know, maybe the fact that we tried to represent an environment which was a little bit more too realistic could have an impact on the user's mental workload. I don't know if that was a question. Sorry.
Yes, no, it's part of the answer. I'm, this is work. Don't worry, it's not a question that there is a right or wrong answer to. It's we're doing science. I'm being very selfish. It's also to do with expectation, right? So yes, uncanny valley. If you'd made a copy of your real lab, not only could it be uncannily different, but they could notice things which had changed, right? So because you didn't get it perfect, they may have brought their bag in with them and put it down on the floor, and it's not in the VR. So don't know if that's tripping people up. I'm just thinking about things that to follow up, that it's very, very hard to control that. We have done the same thing, by the way. Person goes into a lab and put it on head-mounted display, they see the same thing. It's a strategy. It has implications though. Uncanny valley, also trust, because the experimenter has to leave, and therefore you don't know if things are changing. So the virtual reality itself as a medium might have other implications. You don't know it's static because it's not real, right? It could be changing around you, things like that. So I'm not sure it should be 0, but a lot of this is to do with confidence over time, so experience. So were your participants very experienced with VR or naive?
Most of them were naive, I would say.
Naive.
In the first experiment, some of them had a little bit used VR, but most of them weren't regular users of VR.
Okay. All right. So again, it might be their first exposure, and it's again something to know and be very clear about. I have a particular comment about the walking one. You didn't find a difference with the sitting task, as far as I understand, but when they started walking around, there was an impact to the environment. I don't know if you discussed in the paper, but you didn't discuss in your presentation that, of course, they're wearing a wired head-mounted display. So there is a mental task which is trying not to get caught up in it. And I'd be interested in what you thought about a wireless head-mounted display in that situation, and whether or not this mental workload difference would go away or not?
Oh, so one of the main hypotheses we had about the fact that we had an increase of the user's mental workload was because of the absence of a virtual body.
Mm-hmm.
But yes, it's true that while the cumbersomeness of the equipment could have an impact on the user's mental workload. And I guess that ergonomical factors have to be taken into account in order to decrease while the potential mental workload the equipment is going to produce. So yes, I think that having wireless headset is going to improve the user's mental workload. So it's going to decrease it.
And the avatar, what about an avatar? Increase or decrease?
Yes, avatar, I think it depends on many factors. So for the avatars, I'm not going to teach you anything. So you have the sense of control, basically. And I think that if you don't have a sense of agency for the avatars, it's going to have an impact on the user's mental workload. Basically, because you're not moving, it's going to provoke a little bit of frustrations, which is not to be, which is linked to the user's mental workload because of these frustrations, for example. So I guess that the avatar is has an influence on the user's mental workload. And the absence of avatar in the walking task means that the user didn't see their feet, and so they didn't have a visual indicators of where they were walking. What I saw as an experimenter during the experiment was that the user wasn't particularly looking at their feet, but maybe that's something that we are going to do unconsciously at some points, and this might be the cause of why there was an increase in the user's mental workload.
Yes, I'm just thinking through. I would, in the walking task, one of the things you think through is, does the body have any impact? And yes, it does tell you where you are, but so does where does the visual flow. It might just get in the way because it doesn't look like you. When you look down, it's wrong because you don't, getting the foot tracking right. It's more interesting when we come to the flight simulator. So what did they see when they put out their hand in the flight simulator? Do they see an avatar?
We only modeled the hands of the users. So you had the hands on the joystick to pilot the aircraft, and you had the hand which was following the Vive tracker, the Vive controller. So we didn't show the Vive controller, but basically we replaced the Vive controller with the hands. And we tried to make it very natural. So when the user was closing the distance between the Vive controller and the virtual interfaces, they felt that it was the hand that was touching the virtual interfaces somehow.
Okay, so when they operate the radio and the fuel controller, they have to reach out.
Yes.
Yeah. Okay. So so then it's got, obviously makes a difference because the body's involved in the task, and despite the fact that walking involves the body. In the first task, it's not clear what an avatar would do, except that we know that individuals are very different in their assessment of how their bodies interact. So, sorry, I see time is passing already. So let's talk about the third task, the third contribution around this data. So you did actually answer quite a few of my questions about normalizing the data. My main comment in my report was there's probably a lot more here than you've already written up. Right? So this is a very difficult area. Yes. It's a nice piece of work. Nothing wrong with it. There's probably 3 or 4 more papers in the data. So I have one specific thing that I would talk about. It might help if you got the figure up of the mental workload in changing over the tasks in order. I don't know which figure it was in your slide. It may help the discussion. So the main criticism I have is how do you know that this is, if you're trying to keep the mental workload constant, you don't have metrics on the axes of your cube, right? So that when you've got this coding of 0, 1, 0, 1 and 0, 1, 2, there's in no sense does 0, 1 on one axis equal the same difficulty on the other axis, especially when it's 0, 1, 2. So I'd like you to defend the criticism to start off with that when you say it's constant workload, it isn't, because 0, 0, 1 is not the same as 1, 0, 0, because the flying task might be more difficult than the fuel task. Yes, this is the figure I meant.
Yes. Okay.
And there is variation in time, right? So
Yes.
it goes up when there are 2 tasks which are on versus 200 at the very beginning, where it's 1 task that's got a bit harder, but there's only still 1 thing to focus on, right? So defend the claim to start off with. Let's do it adversarial style. That this is constant workload.
Yes, actually, yes, it shows that maybe it was a little bit, to be honest, overclaimed that it was constant workload. It was more meant to be, we tried to build a scenario which was as constant as possible, considering what is the states that we had, actually. So ideally, what we could do would be to consider what is the variations in real time and to try to keep it at the same level, considering individual differences. But in our case, we wanted just to see and to study the effect of, well, the induction processes. So considering the randomized traversal of the state machine or the fixed order of the state machines on the user's mental workload overall, considering that we wanted to have a scenario which was as constant as we could, considering our first experiment. So the data assessment part for the first scenario, which was also not actually very constant.
Right. Okay.
It was very approximate.
There's 2 observations. I wouldn't have called it constant.
Yes.
It's low variance, right? So low variance, the others are high. In particular, the first one doesn't reach the minimum or maximum. That's very safe, right? So it's low variance is one way of discussing it, but also not extremer. That suggests that there's quite a lot more you could do with the data, because you've then got a hard constraint in the, if you've trained on the left-hand data, you don't have, there's lots more to do. There's not a criticism. It's just that in the data, so lots of the data you've got, you don't have a path from low to high. That's going to confuse the machine learning system, I think, because its likelihood is going to be either it's constant or it's increasing, because over time it hasn't seen a decreasing. So it's just that there are things there which you might want to have a think about, especially when you present the training data. There's lots of things you could do. Nothing wrong with the results that are presented, just lots more work to do with them.
Yes.
And the second one is a little bit about the metrics. So again, it's criticism because I think there's more to do, which is that your states are choosing 5. How do you factor out the bias, subject bias, that they'll just change their rating because you've asked them? So subjects, being the lovely people that they are, if you ask them a question, they'll try and give you the right information. And that scale, to me, I'm not expert with it, never used it, just shouts that you should compensate for change. Is that a method, or am I just being too critical of subjects?
No, don't worry. This is something which is quite a lot studied in the psychological field and the statistics. So it has been proven that when you have a scale, users are not going to take the extremes. They are not going to rate at the extremes. So we tend to stay in the safe zone somehow. So with 5 ratings, and we have seen that, especially where we ask users if they were feeling overloaded at some points, that why they wouldn't go towards the 5th rating. And how did we control it? So we did the best that we could, actually. So it was during the instructions part. So we have shown them the 5 ratings. We gave them the descriptions, and we stated that please don't hesitate to rate at the minimum and rate at your maximums when you're feeling overloaded. You feel like that you are behind the task. It means that you are overloaded, basically. And we did that for each of the subjects, eventually, even for the third contributions with the 75 participants. So we mentioned it. So I don't know if it answers your questions, but still, I agree that there might be some bias linked to the fact that we are asking the subject how they feel.
Yes, again, it's because you've got, there's a separate thing here, which is that you've got constant or increasing. So yes, I can imagine that somebody's going to not go to the highest rating because they don't know if it's going to get any harder. I'm reminded of those the gym machines where it goes up and then down. And by the second time it's gone up to the peak, you know what the peak is, like how exhausted I'm going to feel. So you're more likely to rate it. So I think there's, again, that would need more data, but it's a sort of interesting question about how this scale might be improved for future work. Okay, if I've got time, I've one last question, because I am just about the viability of these sensors over time. You've put them in head-mounted display, but your task is quite static. We know they're difficult for moving. So can you just finish by saying, are these going to be practical in future head-mounted displays? Can you compensate for the motion artifacts, or are we? What's your feeling about these sensors? Are they going to progress to the point where they're sort of general use, or is the motion going to just make them difficult outside of the lab?
I'm very optimistic about the sensors. Well, not all sensors, but I'm quite optimistic overall about the fact that we are going to be able to take out motion artifacts and to treat them, to filter them. So in our signals, even for the headset, we already applied some filters in order to take out the noise from the motion artifacts. But yes, we can't really take all of them out, and we can't really know when we still have some motion artifacts or not. And I think that putting the sensors inside the headset is going to help a lot, especially in VR, where we have a lot of hand interactions. We are going to move a little bit using the controllers and interacting with the objects. Already putting them into the headset is going to help quite a lot. But yes, I agree that there's still more work to do, but I'm optimistic about the fact that it's going to be improved in the futures, doing a little bit of signal processing and a lot of studies in this field.
Great. Okay. Thank you. I pass back to the chair. Thanks.
Thanks.
Okay. Thanks, Anthony. So now we go for Daniel Mestre, the second rapporteur. With Daniel Mestre is directeur de recherche au CNRS, donc à Aix-Marseille University.
Merci, Madame la Présidente. Okay. Well, difficult to go after Anthony. First, I want to acknowledge the quality of your work, the extension of your work. I can see that you have publications, communication, and even a patent on your work. So that's clearly signifies that your work is important. And you started tackling a really difficult question, which is evaluating online mental workload in a, let's call it a training task. So as far as I understood, you dealt with the induction, you dealt with recognition. What about the next step, adaptation? How do you see, do you foresee what you could do in this field? Because I think this is the ultimate goal, and this is a difficult goal. Because I'd say my vision of it, if you have a training task, let's say, and you will adjust the difficulty of a task or the tasks as a function of the current mental workload, how do you still guarantee that the goal of training, the training goal, the training efficiency is going to be satisfied?
Okay, that's a very, very good question. And how I see it is that we want to take control over the mental workload, but yes, I agree that we want to fulfill the training goal at first. So what I propose is to put some constraints inside the training and the adaptation parameters. So for example, we want the users to reach a certain task performances for this task, or we want the users to do a specific task, but overall we want the users to have a low variant about the mental workload progression. So we want to have for the users. So we want to have somehow the control over it, and we can make some weights about the different constraints we are putting inside with the control of the scenarios, I think. So you can put some factors, some weight on each of the conditions, and consider the mental workload last. Consider if you want to take into account a little bit more, for example, the training constraints and the training performances.
And also the fact that you mentioned that in your presentation, that was really nice, by the way. if you give feedback about the mental workload, you had a slide on that. Doesn't it contribute to multitasking? Another task, giving feedback is another task, and controlling feedback or not.
Given a task, sorry, can you repeat the question?
Yeah. You mentioned in one slide this point, if you give feedback about the mental workload at the one moment, the subject or not will focus on this information, which is not directly related to a task. How do you do with that?
So if I understand well, if we get the feedback from the task, the user is not going to understand or not that the feedback is directed at him or not, depending. So he's not going to be aware, maybe, that there is a feedback from the task, depending on his or her performances. And the question is, how do we control that the user is not aware of that the difficulty is controlled for him? Is
Okay.
it?
So, if I understand, your idea is to control the task difficulty.
Yes.
Okay. And you mentioned that point too. What about complex environments when you might have different tasks or subtasks? How do you do it?
Well, we did a very pragmatic things in our second contributions, and we consider all of the possible task configurations. So we did a map of everything which was possible for the task, and we controlled the link between each of these tasks, and we wanted to go towards them. So I think that, well, we have to, the thing which is the most important, the first step, is the structure of the environment, the taxonomy we are going to use in the environment, considering, for example, information about the task difficulty, which was what we did, but also different things. So, for example, the virtual agents behaviors. So if this is something that we want to control, we have to structure the environment depending on that. And after that, we have to give a priori knowledge about the mental workload this information are going to bring to the user's mental workload. And based on that, we are going to be able to modulate the scenario given the training objective and the mental workload objective for the users. So I think it's a question of taxonomy and how we structure the environment and how we consider the subtask in the graph. I don't know if that answers your questions.
Yeah. No, it's a difficult one. Just one point that I have to mention. In your state of the art, you mentioned the role of presence. And you don't really use that in your work. How come?
Oh, okay. So in my state of the art for the presence, so my state of the art was very overall with affective and cognitive states considered. And there was a lot of work on emotions and presence, not that much about the cognitive performances. We didn't really measure presence because what we wanted to do was to try to modulate the user's mental workload. But I agree that this is something that we could consider in the futures because while presence is quite a lot linked to very important factors, so engagement and emotions, and these things can impact the user's mental workload over time. So we want to keep the users engaged, but that's not something we have considered actually. But that could be interesting in the future.
What gave me this question was your slide with a flight simulator, where, and we had this experiment doing a helicopter training. If the task becomes too difficult, the subject will disengage. And I think this is a problem in itself. It can be a control. But anyway, this is not my question. My question is, at the end, do you want to rely on behavioral indicators and physiological indicators, or do you still believe that subjective feelings are important in your model?
I think that subjective feelings are very important. at least in the end of the experiments, to study the user experience, to see if finally, how did they feel, how did they perceive the task difficulty progressions. I think that's still very important. But in the end, honestly, I prefer objective measures, to be honest. But I know that using only objective measures today is quite difficult because you have, well, a lot of noises, a lot of artifacts. And today, maybe what we consider the ground truth was to take into account the user's perceived mental workload in an ecological situation where the user is likely to move a little bit and to make noises in the physiological signals. But in the end, ideally, if we can detect the user's mental workload level without asking them how they feel, that would be fantastic, I think.
Yeah, of course, of course. Just a small point is, I appreciated your use of the ISA. Tell me if I'm wrong. As far as I understand, it's got the advantage of being, contrary to postdoc questionnaires, a continuous measure. Okay, so you ask every 2 minutes. Is that right?
Yes, exactly. So the scenario lasted 2 minutes, and we asked them how they feel every 30 seconds. And it depends on the protocol we are talking about, but yes.
But why did you report only mean values and not use the evolution of the values all the time?
Okay, so we recorded everything for all of the users, so the progression of mental workload for each state over time. But what we presented was the mean average of mental workload induced by each of the states. So I'm just going to show the slide. So yes, we decided to take into account the average because it was easier to explain what was happening. So in the PhD manuscript, so I showed the mental workload level distributions for each of the states, which was very interesting to see that we had a little bit of variance between each of for each state for the mental workload experiences by the users. But yes, for the presentations and overall, what we wanted to see was the relative difference between each of the states overall. So we relied on the average because it was the most obvious thing to do, actually, to take into account this kind of measures. But I agree that would be interesting to consider individual differences and the progression of each user in the state machine.
No. It's your specialty, not mine. Considering physiological parameters, do I have time? Yeah, don't keep track of time. You mentioned also using EEG, FNRIS. Don't you think there could be interferences between the HMD and EEG, for instance?
So honestly, I'm not an expert of BCI and EEG, even if I'm surrounded by very expert of BCI around me. And yes, I know that for sure that EEG measures can have very easy emotion artifacts. And so contact with the headset and potentially the head of the wet headset could show some interferences with EEG measures. I think that's possible, yes, compared to if they didn't have a VRHMD on, of course. If we want to compare different conditions with VR headset and the EEG, I guess that we can somehow control the effect of the different conditions. And we could try to have, well, a neat physiological signals of the EEG. I hope that's going to be the case in the future, at least. But I know that it's quite difficult today.
I know. Concerning oculomotor behavior, you use mainly pupil diameter, right?
Yes.
Why don't you use eye tracking for, I don't know, looking what the subject is focused on?
That was a choice. So what we tried to do, So basically, it's many development times, which is at cause of the reason why we only consider the pupil diameter. So we wanted to have access to the Vive Pro eye tracker. And for that, it took quite some time to develop a program to try to detect the blink. We wanted to take into consideration the blink and the fixation durations, the saccadic movements, which we know have a lot of impact, which are not impacted by the user's mental workload, but it didn't really work well. So we decided not to consider them in the ISMAR study, in the contributions. But we agree that this is something that we should consider in the futures because those have been found to be very interesting measures. But the reason is mainly time and development time.
I appreciate that, no problem. But I mean, if you more or less focus on training tasks, you will have to consider eye tracking as an indicator. Where
yes, I agree.
And I'm also puzzled about the use of pupil diameter. Well, maybe if you are in a HMD, well, seems like you can use it efficiently. But what about being in a cave system? You mentioned a cave system, and in tasks where the luminance level is going to change a lot. That I mean, using pupil diameter for mental workload is okay, but I think that pupil diameter varies with other parameters.
Yes. So this is kind of a frustration for me too. So I was quite happy that we managed to consider the pupil diameter, but something that we should consider in the future, because we know that we have an impact of light on the pupil diameter, is trying to control the amount of light in what is the headset and outside the headset, for example, in cave-like system. And I know that it can be a little bit more difficult to get these informations in cave-like system, but yes, I agree that this is something that we have to control in order to make sure that we only extract that data from the mental workload.
Okay. Last question, just as for fun. You mentioned 65% recognition on average. Okay. What's missing?
Yes. What's missing? That's a good question. So basically data, I would say. So that's a logical explanation to all bad that we have in machine learning. If we had more data, maybe we could improve the mental workload recognition accuracy, but that's only a supposition. We can't be sure of that. We tried to normalize the data as much as we could, considering all the information that we had. But yes, I think data. That would be the most obvious response.
Yeah, good answer. Well, that's it. Once again, thank you for your work. It's really an important piece of work in our field, and I wish you the best for future.
Thank you.
Okay, thanks. So now we go with the examinator. So with Mark Bellyhurst, who is professor at the University of South Australia. Mark?
Hi there.
Yeah.
Can you hear me okay?
Yeah, yes.
Great. So I just had a few questions. First of all, thank you for the presentation. It was very, very interesting. I wanted to ask about the first experiment. So your first experiment was mostly an audio task. You know, they had to be in the VR, but then they had to do an in-back, which was audio. So do you think that you would have had different results if the task had been more visual? So for example, a visual search task in the real world and in the VR?
I definitely think that the nature of the task is going to have an impact on the user's mental workload. So I think, well, this is only suppositions again, but yes, because in VR, you have mostly visual feedback of the world.
Right.
You are going to be a little bit more conscious about the differences. So you are going to have perhaps against differences in perceptions about the visual objects in the virtual reality compared to in the real world. So I think that might impact the result we would have if we had used a visual task, yes.
Hmm. And because in the second experiment, you said that one of the reasons why there may have been a significant difference between the VR and the real world is that they could see their the body, well, they couldn't see their body in the VR case anymore. So in that case, you'd taken the visual cues out, and then you saw that had an impact on the mental workload measures.
Yes, I think that might be the case, but this is also discussions, so it's also subjective. But what I've seen in the past is that while the sense of embodiment can have incredible impact on the user's cognitions on different levels, so you have a lot of things which have been studied, for example, the sense of the engagement. And I think that, yes, the control or the presence or not of a virtual body or different sense of embodiment factors could impact the user's mental workload as well. Yeah.
And then I was also curious with the second experiment. So the first experiment, you had captured physiological cues, but in the second experiment, you didn't do that. I was wondering why you decided not to do that in the second experiment.
For the second experiment, we didn't use any visual cues. In the second experiment, sorry?
Physiological cues. In the first experiment, you had measured the heart rate and you'd used the shimmer.
Yes.
In the second experiment, you did not use the shimmer. So I was curious why you made that change.
Originally, we just wanted to push a little bit further the experiment. And we found out that only considering the walking test, we had a small effect. So it was a p-value equal 0.05, so it was very small. And I wanted just to push the experiment a little bit further. And well, the reason why we did the VR headset with integrated sensors was because it takes quite a lot of time to install the sensors on the body, basically. So we wanted just to do a quick experiment to push the experiment further. So we didn't take into account in this case just the physiological sensors because it wasn't the hypothesis we wanted to test actually in the second one.
Okay. Because I guess that would have given you some more cues about not just the subjective measures, but also more objective measures of people's workload as well. So,
sure.
Okay. And then I wanted to talk about the experiment. I guess it's experiment 3 with the flight simulator, where you were able to have different combinations of workload depending on the combination of tasks that you had. And actually, I had a similar question to Anthony, but I won't ask that now because he already made the point that they may not be equal. You have this very nice matrix, but it may not actually be the case. But also in this experiment, you also chose not to use any physiological cues. Is that right? So they didn't have the shimmer or any other device to measure their workload. Is that right?
Yes, we didn't measure any physiological measures in the second contributions. So basically, we wanted to structure the virtual training environment to make scenarios which were able to modulate it. But yes, we didn't collect this kind of measures. We saved it for the following.
Anthony made the good point that you may have had some bias because of the survey. So if you'd had that extra measure, you may have been able to check to see if there was some bias or not, because they may be able to, the results may be skewed a little bit because of the survey, but the physiological cues would have given you a good measure of workload regardless of that.
Yes.
So then I wanted to ask about the last experiment with the machine learning. Actually, I guess the question's already been asked, but you got 64% or so accuracy. What do you think, what different things could be done to increase the accuracy? Because, I mean, it's better than chance, but it's still not 80% or 90%. So can you think of any things you can do to increase the accuracy?
So we did different things. So I still think that having more data is going to help quite a lot. We test out some normalization methods. So I know that we try to take into account potentially the individual differences, considering that for the same mental workload device, users will have different physiological responses. So we had min-max normalization methods. And we tried to consider also the physiological signals while they were resting during a baseline. But I think that maybe we could try to push the signal analysis a little bit further about the signal processing. So by either trying to normalize a little bit more or trying to explore a little bit more the normalization methods for the signals, or by trying to take into account the individual differences between the perception of the users between their minimal mental workload score and their maximal mental workload scores compared to the other users and compared to their physiological signals. I don't know how to do that, actually, to be honest, but that's definitely something that I would like to consider.
Okay. And what about capturing some other types of sensor data? So, for example, you could use the EEG signal and measure some brain activity or some other data, maybe face expression or some other, because you really only had several data sources that you didn't get a wider range of data. Do you think that would help as well?
Oh, yes, definitely. I think that adding a little bit more sensor is going to help quite a lot. But meaning that we have a lot more of sensor means that we also have to get a lot more of data. So it's finding a good trade-off. But I agree that having more sensor is going to bring a lot more of information about the user psychological state. So yes, more ocular activity features, for example, and BCI features, definitely.
And I was interested at the end of your presentation, you talked about this new kind of new field of VR, like affective and cognitive VR, and which your research is in the area. So I want to imagine now that you are several years after your PhD, and you know, maybe you have got some funding or a grant, or it's now the opportunity that you can pick your own research topic. So what do you think in this new area of affective and cognitive VR, what do you think would be some of the most important topics to study?
So I definitely think that finding a way to develop methods of inductions, battery of task, so sort of making an IAPS. So IAPS is so a database of image which were found to induce specific emotions on the computer screen. I think that doing the same things for VR is definitely something that we have to look out for. The recognitions, definitely, because while VR is very powerful, so it can engage users, as I said. So trying to use these informations, the users' affective and cognitive responses to try to improve the recognition model is going to be very important. And for the exploitation, well, there are so many use cases, but the most obvious one, I think, which would benefit eventually from these works is, for example, the educational field, taking into account the user's cognitive load and trying to make learning more efficient for the students and make them engaged, well, trying to bring them into a specific field and making them want to learn using gamifications and other VR paradigms.
So yeah, I'm quite familiar with the IAPS picture set. So what you're saying is that you could imagine a VR version, so maybe a set of VR environments, and in these environments, people experience a certain amount of workload typically. So you can use that as to provide the same kind of gold standard that IAPS provides. Is that what you're imagining?
Yes, exactly. I would think that that would be amazing to have scenes which can induce specific mental workload levels or specific emotion levels, specific emotions to users. Yes.
Well, that's almost what you're doing with your flight simulator. That's great.
Yes.
And then just one last question. I guess I'm just looking at the slide you got on the screen now. It's a little bit different, but in the beginning of your thesis, you had another picture that showed the adaptation of the or close the loop, basically using a reactive virtual environment. And but in your thesis, you didn't really do this. You had the real-time recognition happening, but then I'm just looking at your thesis now. It's I think it's figure 1 or 2. Just not sure. Hang on. Just trying to get down to the point here. Oh yes, so it's figure number 2, and you've got a dotted line between the model, MV recognition model, and the virtual environment. So you don't, you never made a VR environment which was adaptive. So if you were to do that, what do you think would be some of the important things to consider in designing an environment like that?
So what I wanted to do, so exactly. We had a dotted line just here after the exploitation, between the recognition and the exploitations, and that would have been great to merge them together. So what we would have tested, I think, would be the timing of adaptations. We would like to test these kind of things. And of course, the outcomes of the exploitations to see if the users are actually going to enjoy a little bit more. So in terms of user experience and engagement and learning outcomes, what are going to be the outcomes of making an adaptive virtual environments. So I think that's, yes.
You could use it for also for training. So you could make sure, for example, you have a training experience, and you could make sure that the person who's training keeps their mental workload at a certain level, because they don't want to have, if it's too much, then they will give up. And if it's not challenging enough, then they may not learn anything. So being able to have the adaptive piece could be very helpful for that type of training application, maybe.
Yes, definitely. I think that would have been our main use cases if we did more user studies. So trying to keep the users' mental workload not too much and not too low to keep them engaged. Yes.
Okay, I think that's all my questions now. Thank you very much. And I'll turn the time to the next person. That was great. Thank you so much.
Thank you.
Thank you, Mark. So now it's going to be my turn, and after it's going to be your advisors. You have 4 of them, so they're going to talk, the 4 of them after. So first of all, I really want to thank you for your document as well as your presentation. I found it extremely interesting. It's not exactly my area of research, so I may have some naive questions, but I really appreciate the effort you've done for presenting your work in such a clear way and also your contribution. So I'd like to continue discussing a bit the topic that Mark has started on, the link between mental workload and emotion. You mentioned it quite a lot in first chapters, background and all that, but after you don't mention it at all in your whole PhD document. You don't refer to it. However, when you answer some of the questions to Anthony and to Daniela, you talk about stress level, frustration. So you use quite a lot of emotional terms. And we also know that physiological data has, it's very much linked to the emotional state. So I would like to hear a little bit more of your point of view on the relationship between this mental workload, task, and emotions, please.
Yes, so thank you first. And yes, I agree. So this is something which took me a lot of brain out at the start of my PhD, trying to find out what was mental workload and the link between mental workload and other psychological states. And yes, so there have been studies which tried to link all of the states together. So what we know for now is that mental workload measures are going to be quite related to the emotional arousal and to stress. So we know that mental workload is very close to cognitive load from the educational field. And yes, the issue with all these definitions, even if they all target a specific context often and specific applications, is that they kind of overlap between them. I agree. So everything is a little bit linked together, and physiological responses can come from different psychological states. And yes, trying to divide everything and to make sure that we are measuring the good things is a difficult task, even if thankfully we have a standardized task to try to induce them and good measurement methods to do so. But yes, basically everything is linked together.
Yeah, absolutely. I think it's a strong fight, and it's not so easy to disentangle of them. But
Yes.
quite interesting to understand it a bit more on how arousal level can impact and may have an effect on, especially for predicting mental workload. That's something. And
Yes.
regarding that, I had a question of this notion of task. So you mentioned several times that sometimes task performance didn't have so much an impact on your result. However, those were naive participants. You use flight simulators, and from what I understood, they were naive in the sense of not used to, not very good at using VR. Some were game experts, others were not, and they were not pilot. So the impact of the task performance may differ from if you were really a pilot trying to train. And so what kind of effect you think you could have on your result of your experiment? I mean, how the impact of really learning and performing right in your task affect the mental workload? That would be my question.
So I definitely think that there are great individual differences between users, and that these individual differences are going to do so that one specific task or state is going to induce different mental workload levels to the users. So for the 75 participants contributions, so the one where we trained the recognition models, what we were interested in was mainly the link between the subjective mental workload and the physiological signals. So yes, you have individual differences, but we wanted to predict the user's mental workload level independently from their profile. So that's why we did a generic recognition model. What can I say more about that? Yes.
Yeah, I mean, just for example, just imagine that in this experiment, you had also a pool of people that really wanted to train to become a pilot. I mean, I don't know if the flight simulator, what was that the goal? Do you think you will get the same result?
No, definitely. I think that engagement inside the task is going to influence the user's mental workload. And hopefully they reported the mental workload level they felt. So one thing that I should mention too is that during all the VR flight simulator task, each time we did a training task for the users, 10 minutes, where we were with them, we gave instructions and they had to do each of the tasks and we explained everything to them. So we tried to make them actually reach a certain understanding level of each of the tasks to be familiarized with the VR devices and the VR interactions. And yes, we do agree that this is important before doing the data assessment part. And yes, I think that you have pools of users and that you have an effect of the user's profile on the user's mental workload and engagement part. But this is, well, we were most interested into between the link of between subjective mental workload and physiological states. But still, this is something that we tried to control in other experiments. So I did try to see if there was an effect of VR expert between VR non-expert on the user's mental workload, on the user's mental effort, for example, in the first experiment. So I didn't present this result because they were non-significant or the statistical power wasn't enough to prove anything. But this is something that I looked out for, yes.
Okay, so if I understood right, your last point, because it was one of my questions, is that you didn't find any statistical differences depending on the level of expertise, either in VR or in games, with your result, especially also for a case study 2. Is that what you're saying?
Yes, but we had very few VR experts in our experiments.
Okay, yeah.
So it was quite hard to see anything.
But you had game expert.
Yes.
You mentioned like 20-30% were.
Yes. So we tested the different conditions. Yes. So it was, I think, the second experiment of the first study that we, yes, exactly. The mental workload level wasn't significant. No, we didn't find any effect of the game experience on the user's mental effort, if I remember well. But yes.
Yeah, oh, that's good, because like that you can somehow take away a variable.
Yes,
we would expect to be an important variable. I have it's more a question. I mean, I'm not sure I understood completely. For when you built your models in for the third study, the last chapter. So if I understood right, you extract the physiological data for 30 seconds, and I don't know, remember, at certain point, okay? So it's not continuous. So there's times where you don't extract data. And I was wondering, am I correct? Or, yeah.
Yes.
So I was wondering, so it looked like you doing this extraction at very uniform steps, but it could be that an important event happens in between this extraction. So I was wondering if having an extraction which could be more event-based, because I mean, you somehow may predict where you could have an event with your simulator, which is much more difficult than in real life, but would that change some of your result? The accuracy of the model?
Potentially. So we really wanted to label our data because we wanted to predict the user's subjective mental workload score. So this was always our references for the timestamps to take the 30-second times just before the subjective self-report. But if we took into account each event inside the flight simulators, it would mean that we would predict somehow the events inside the flight simulators and potentially when the task would be activated or deactivated. So I think that would be interesting to see if they have an impact on the user's mental workload. But and that could be actually the case. And the idea behind why we did it in a very punctual way when we trained the models is because we wanted in the end to be able to measure the user's mental workload in a continuous way and to detect at which point actually we had an event and whoa, the user's mental workload level went up at this moment, and we can say that it was at this point. But yes, in the end, that would be quite interesting to detect them.
Okay. So I have one more question regarding, so every 30 seconds or you ask people to answer in which mental workload they are. Don't you think it's very, I mean, you interrupt the task all the time. Isn't it a workload by itself to answer every second?
Yes.
Yeah,
definitely. So this is basically a forced task, the ISA self-report. It was very intrusive. I agree with that. But yes, that was one of the worry we had when we did the experiment. And we tried to maintain how we made the user see the ISA, so the transfer the ISA in a very same manner between each state. So they always had 3 ISA scores to self-report at some points for each of the states. And we measured the impact of the states on the ISA response time to see if the ISA did influence potentially the mental workload scores, and if the state did influence the ISA response. And we didn't find any effect, hopefully. So that was a good thing. But yes, this is intrusive. But normally it didn't change anything between the states. So it was very constant. It was the same amount of mental workload which was added for each of the states.
Okay, that's really good for you, for your
yes.
for your work. Yeah, and so that's my last question regards. So you say, and I fully agree that the more you have data sensors, the better you can learn a model. However, when you have more sensors, it's quite common that sometimes you have contradictory. I mean, they are all not go in the same direction. So fusing data is a very complex task. So I was wondering if you thought of that. Okay, the more is the better, but at the same time, it makes life much more complex. So what would be a good trade-off? Because you have quite a lot of experiences now in this field of how much new sensors you could bring in.
So definitely, so we tried to select the number of features to see if some of them were actually irrelevant for mental workload. So we did the principal component analysis, but using the random forest algorithm in machine learning, we found out that actually taking out some CES features, which didn't really help, decreased the mental workload recognition accuracy. And in real time, we had a very slow, very little latency considering the features we considered. So we had about 70 physiological features, and we had maybe 20 milliseconds of latency in the recognitions in real time. So we decided to consider all of them. But if we want to take more data, I think that we could consider to decrease the size of the features to extract only the relevant one by doing a principal component analysis, probabilistic and deep learning methods apply. Yes.
Okay. Well, thanks a lot for your questions. And I think now you're going to relax a bit more. Now we turn the time to now your 4 advisors. And I propose to start with Ferran Arguelaguet, qui est chargé de recherche à INRIA de Rennes, Bretagne-Atlantique.
So thank you, Ms. President. So first of all, I would like to thank all the members of the jury for being there. It's a pleasure. Of course, it would have been better to be in place, but well, this is another story. So also, I would like to thank you, Tiffany, for keeping my mental workload high but not overloaded during the entire presentation. I think you did a really nice job there, and I think that your presentation was getting better and better during the rehearsals, and I think that now you really nail it. So thank you very much for this. So I would say I also have the honor of knowing you a bit more than the other members of the jury, because you did a 6-month internship before starting your PhD. So I have maybe the chance to work a bit more on, with you, and also see all your qualities in terms of human qualities, development qualities, research qualities. So I think that you have really all you need to be a really good researcher. If you would like to stay in the public research of, who knows, maybe on the industry. So, but of course, this is really your choice. So I also would like to thank to other members of your supervision. So Nicolas, Anatole, and Guillaume for allowing me to be somehow in this nice trip of 3 years with you during this exciting topic. So I think I learned a lot of stuff, and I hope that you also learn a lot of stuff from us. And maybe I just maybe talk about this affective cognitive basically scope that Catherine elicited at the beginning. So you know that Tiffany, she really wanted to work on the affective. She was really her dreamer, her driver, and she really wanted to do that. And for several reasons, at the end, the scope of this PhD was focused on mental workload, but she somehow managed to keep this urge at pace, and so she really worked on the cognitive aspects and this mental workload. But we clearly see that all of the work is these touches of affective. So I really hope that in the future you will be able to work on this. And of course, I really wish you the best for the future endeavors in Switzerland. So to add some spoilers to the other members of the jury, and I think I will let the other supervisors to comment. So thank you.
Thank you. So now, Martin Nicolas, with ingénieur de recherche à IRT Becom Rennes.
Yes, thank you. First, I would like to thank Anatole and Ferran for giving me the opportunity to supervise this PhD. It was the first time for me, and it was a very great experience. It was very pleasant to work with you during this last year. And now let's talk about you, Tiffany. I will don't ask any question. I have 3 years for that, and it's not the moment. I just want to congratulate you for this work. It was a very great job, great work. Today, as Ferran said, you made a very nice presentation. You managed to keep a reasonable pace, so well done. And I already tell you that you improve a lot during this last year. You can be very proud of yourself. It's very good. It was very good to work with you during this time. I learned a lot with you, with Anatole and Ferran. It was the opportunity to publish several papers in very good high venue, so it was really great. For me, it was a great collaboration. You have already know how to move forward and to be force of proposal on the very large of topics. So it was very, very interesting to work with you. I hope you are not too disappointed to not able to test all your ID during this last year, especially on the Yerkes-Dodson law on the flow. but yeah, you are very competent. I am sure you will continue to do very good scientific work in the years to come. So I'm pretty sure that one day you will be able to work on these topics. And to finish, it's sad to not be with you today to celebrate it. But it's like that. But congrats, Tiffany. I wish you the best for the future.
Thank you.
Okay, thank you. So now, Guillaume Gégou, responsable de laboratoire à IRT-BCom.
Hi. So thank you, Tiffany, for your very interesting presentation. It was a very good presentation of all this work for your FIDI. I would like also to thank you, and also to thank the whole team, and to notice the scientific management in this thesis, and very interesting publications, very interesting things have been done in this thesis. And the link, one thing important for a thesis in BCom is also the link that could be done between this scientific work and some potential application in the industry. So, it was very interesting to work, for example, on the simulator, on the aircraft simulator, because we have some clients, some contact with industrial companies that work on this field, and the work you have done on your thesis is very important for the future of research and development, and this field of research, but also to work with industrial, and to show that we invest in this very interesting subject. So thank you very much. Thank you to the whole team. And I also noticed that you have also very interesting conclusions or some hypotheses for the future, for future studies. And it's very important also because we have done this study, this thesis, but we will work in the future for some other things, and to perhaps generalization and so on. So your conclusions, your hypotheses for the future are very useful also for the activity. So thank you very much.
Thank you.
Thank you. So now we are going to ask Anatole Guillet, which is a directeur de recherche à INRIA de Rennes, Bretagne Atlantique.
Oui, merci Madame la Présidente. Thank you. Et félicitations Tiffany. Merci pour cette belle présentation. First, I'd like to thank also the jury members. It's a real pity that we could not welcome you in Rennes, and I think it's the third or fourth times I'm saying this in 2 months or 3 months. It's even more a pity, and I think Mark and Anthony, you are serial rapporteur or examiner for our juries. I think I owe you like 2 or 3 restaurants already. I hope that we'll have a chance to pay our debts in the future.
Yes.
Catherine, thank you for the extra amount of work and extra amount of paperwork due to the pandemic. We have lots of remote papers to do. Anthony, Daniel, thank you for your reports. I know you were extremely busy with other duties. And Mark, thank you also for staying so late for this PhD jury. I'd like to thank also the co-supervisors, as already been said. First, Guillaume and Become for reacting really fast 3 years ago. You reacted fast to grasp Tiffany because we had unfortunately an unexpected dropping of a funding, and you reacted fast and you accepted the challenge. This is our first collaboration with Become, and I think it's a really nice success to start with. Nicola, it was a great collaboration. It's been a pleasure to work with you, and the PhD would have been very different without your skills in machine learning, in data analysis and psychology. And Ferran, I think we are an old couple now. But it's always a pleasure to work and collaborate with you. I'd like to thank also the public, the audience. I think we had like a bit more than 40 people connected to the YouTube channel and streaming today. Thank you for being here. And I think you have some messages in the chat window you can check later, Tiffany, from your family, your former colleagues. We're all enthusiastic. Tiffany, you grasped a challenging topic 3 years ago. We were starting nearly from scratch. It was a challenge for both Become and us. It was funny for you, I think, to work on workload, stress, and emotions, management of emotions, since you are globally generally quite stressed and and actually super stressed at some periods, extremely demanding with yourself. And I hope that with this PhD now, you learn to progressively manage your workload and manage your stress over the years. I can stress your qualities. You have impressive working capacities, very dedicated, very reliable to your work and to your colleagues. Once you are convinced, because if you are not convinced, it takes some time for you to start working on a topic if you are not convinced. And you are full of surprise because we discovered that you're also a great computer graphist and artist, and also a specialist of martial arts and a champion in martial arts. So that's also maybe another reason why you can control your stress in the strategic moments. You're a great teammate, very helpful with the others, well integrated, notably participating very successfully to the hackathons, VR hackathons. We were quite involved in 3D UI contests over the past years, and you have always been there and a great teammate. So now I think, yeah, indeed, you'll be able, I hope, to relax, to breathe, to enjoy a bit this moment before actually you fly or you move quite rapidly to Switzerland and ETH Zurich for your postdoc. But in any case, we'll be happy to welcome you back here in a better situation, hopefully, and happy to continue to exchange and collaborate in the future. I wish you really all the best for your personal and professional life afterwards. That's it for me, Madame la Présidente.
Okay, thanks. So I think now the time is for the jury to deliberate. And for that, we're going to go to another room, video conference room, and we come back for the announcement. Okay.
Can you put the link for the room in the chat window again, please? Sorry.
Yeah.
maybe I close to wrap it my session and maybe someone missed the link.
Yeah. Is everybody here?
Missing Mark, I think.
Missing. Okay, just waiting for Mark.
Okay, so I think we're all back here now. And so Tiffany, the jury members have gathered and discussed about your presentation and your work. And I'm going to read the small report that will be written in French, but I'm going to translate it in English, so bear with me with it's a mix of language. And the jury want to highlight that you have done a very clear presentation, very well illustrated, and with a lot of pedagogy, so that allow you to describe your complex research questions and also approaches. You were able to show important contribution in a domain which is highly pluridisciplinary, such as that involve computer science, cognitive science, virtual reality, socio-affective computing. You also did an amazing quantity of work that involved building hardware, developing software, conducting, and that is the most important, many highly controlled experiments, as well as building computational models that involve also machine learning. The answer to all the numerous questions of the jury members have shown that you mastered your domain, as well as you have a strong background, scientific backgrounds that allow you to have good argumentations. And the discussion also shows that you're highly engaged in your topics and you have a lot of scientific maturity. You also managed to have a lot of publications during those 3 years, as well as a patent, which is really quite amazing. And pour toutes ces raisons, le jury décide de vous accorder le grade de docteur de l'Université Rennes 1 dans la spécialité informatique. So, bravo.
So I have some acknowledgement to do, and I will start in English. I'm cheating a little bit. I have written part of the headline because I don't want to miss anyone. And I will just end in French. So first, I would really like to thank the jury. I am very grateful that you took the time to evaluate my work and to read the manuscript. This is really an honor for me to have you evaluating my work. And I would really like also to thank my thesis supervisors. So Anatole, Ferran, Nicolas, and Guillaume. I know how lucky I am to have such outstanding researchers and available researchers as supervisors. And for the engineers, I am very grateful that you accompanied me during this PhD done in a company context, which is a little bit special. So thank you for the trust and the autonomy you gave me. You gave me very good advices and I learned a lot, really a lot during the PhD, and I owe you a lot for that. You're amazing people, patient, good pedagogues, and I would really like to thank you for the good mood behind the meetings and everything you taught me. I would like to thank Florian and Diane for helping me with the broadcast of the presentation today, so it wouldn't have been possible without you. So we can see Florian in the background. And I'm going to switch in French for the following part. Donc, j'aimerais remercier mes collègues, donc anciens et actuels, que ce soit à l'INRIA ou à DICOM. J'ai pu collaborer avec des gens avec des profils très différents de ce dont j'avais l'habitude auparavant. Donc, sans vous, notamment Nicolas, Jean-Marc et Martin, la transition vers le domaine de la psychologie et de l'ergonomie depuis l'informatique et les mathématiques a pu se faire tout en douceur. Et ça, je vous en suis très reconnaissante pour ça. L'ambiance d'équipe, notamment à l'INRIA, a été absolument géniale. J'ai passé 3 années très riches à discuter avec vous tous et à débattre sur des sujets et d'autres. Donc, je ne peux pas malheureusement mentionner tout le monde. Donc, il y a beaucoup de noms, beaucoup de personnes qui m'ont marqué, mais j'aimerais donner quelques mentions honorables. Donc, merci à Kim, Victor, Xavier et Alexandre. Donc, que ce soit pour nos débats ou nos blagues sur les BCI, les interfaces à retour haptique, le post-processing, les nuits blanches de développement en mode hackathon, ou les soirées couscous, burger, One Piece, dessin et jeux vidéo. Et merci aux participants, bien évidemment. Donc, mes expériences ont rencontré un succès écrasant. Donc, je n'ai pas du tout eu à avoir à batailler pour amener des personnes sur mes expériences. Et ça, c'était super. Je pense que c'est exceptionnel en tant que thésarde. Je tiens évidemment à remercier ma famille, donc que ce soit celle qui est proche ou celle qui se trouve aux différents coins de la France ou du monde, qui, malgré le flou obscur sur ce que je fais, où est-ce que je me trouve, je sais me soutiendra toujours et c'est réciproque. J'ai la chance d'avoir pu mener à bien mes études à bien, faire ce que je voulais, travailler dans un domaine qui est absolument génial, donc un croisement entre la cognition et la réalité virtuelle. Et ça, c'est en bonne partie grâce à mes parents. Et j'aimerais remercier aussi mes frères qui sont vraiment formidables. Je sais qu'ils gèrent énormément, donc Anthony et Christophe. Et j'aimerais remercier aussi Mathieu, donc mon copain qui a toujours su trouver les bons mots et m'encourager dans la bonne direction. Merci.
Bravo. Félicitations, docteur.
Merci.
Félicitations, Tiffany.
Félicitations.
Merci.
Bravo.
Bravo, félicitations.
Voilà.
Merci à tous. Je crois qu'on est encore en streaming là. I think we are still in streaming. So thanks you everybody for being here. And thanks to the jury again. It's a pleasure to have the chance to have these really fruitful exchanges. There were lots of super interesting exchanges and discussions. So thank you all for being here. Mark, I think it's getting a little bit later and later now in Australia. Thank you for being here. Your mic is mute. Huh? Yeah, your mic is mute if you're on.
Sorry, thank you, and congratulations again. It was a really great presentation. It's not too late for me, but it's nice always to have a good presentation. So you did a great job, very good job. Thank you so much.
Thank you.
Okay.
Thanks, Anthony. So I didn't count, but it's been a lot of PhD juries for you. So I really hope that the next ones will be maybe with more food at the end.
With lunch would be good.
Yes.
The same for Mark, for Daniel, Catherine. It's also a pity that you are not here, but a pleasure to see you too. And looking forward to meeting you in presence.
Sure. Looking forward to drinking something.
Yeah.